Okay, sorry about the holdup here. We're having some kind of technical glitch. All right, for those of you online, it looks like I'm going to have to take this meeting down, and I'm going to try to restart it. So if you just log in again in just a minute or so, we should be okay. Oh, here we go. All right, scratch that idea. I think maybe. Maybe we're going to be okay after all. Okay. Looks like the document camera giving a bit of trouble. Okay, there's one other thing I can try. Well, this is a new experience. Well, what do you know? All right, sorry for the delay. Just now, I think, all right, we're back. All right, tonight, we want to talk more about systems of equations. And in particular, we're going to be looking at two things, or maybe I even should say three. First of all, I'm going to talk about how you can take a linear differential equation of the kind we were looking at before, and we'll be concentrating on these second order linear with constant coefficients and 0 on the right hand side, homogeneous. And I'm going to show how to translate that to a vector differential equation. And A is a matrix of coefficients, which is related to this A and B. It's not simply A and B. I also want to show how to solve the system, which actually you've seen before, so I won't need to say a lot about that, but what we're going to do is solve it both ways and show that you get the same solution with either approach. I also want to introduce what's known as the phase plane. And the phase plane allows us to look at points of equilibrium. For this system. Now, in the case of this sort of system, there's always only one point of equilibrium. It's the origin. But with nonlinear systems, you can have more. So it makes sense to start with the one that's simple. And when we look at these points of equilibrium, we're going to be doing some work classifying them. And we're going to classify them according to their type. And we're also going to classify them according to what we call the stability of the equation. So that's the agenda. I do not have printed notes for this. This is actually the first time I've put this material in this course. So the notes are not quite up to date with what's going to be happening on the ground here. And I have, I believe, a list of examples I want to work through. So mostly I'm going to do this, I'm going to do this by working through several examples, and I'll be showing you how to do the classifications and try to indicate some sense of what they mean as we go through it. So there is a little bit of theory, but it's introduced by means of example. So the first thing that we want to do is we want to talk about this class of equations, and we want to be able to translate that into a first order system of equations. So this is second order. We're going to translate it into first order system of equations. And in general, at least for linear equations, if you have an nth order linear ordinary differential equation, you can always translate it to a system with n variables, but is first order. So this is also another explanation for why we didn't dig very deeply. Oh, that should have 2 primes on it there. We didn't dig very deeply to third and higher order equations. And the reason is most of the time that they're studied, they are translated to systems, linear systems, rather than to study them in this form here. Okay, it turns out that you do this with a really simple change of variables. We're going to have two variables, y1 and y2, and y1 is going to be just nothing other than y. y2 is going to be the first derivative of y, which of course is also the first derivative of y1. And y2 prime is the derivative of y2, of course, but that's also the second derivative of y. And it's also the second derivative of y1. Now, if you apply that, just make those substitutions here in this original equation, you end up with generating what you need for a system. So y double prime, that's what I'm going to call y2 prime, plus a y prime, but y prime is y2, plus by, but instead of y, I'm going to write y1. That's equal to 0. And what I want to do is solve this for y2 prime. So y2 prime is equal to, now all this stuff is going to the other side of the equation, so the coefficients become negative. But I want them in the order of, in numerical order by subscript. y1 on the left, y2 on the right. So this goes over to the left as minus b y1 minus a y2. And then we have our other equation, y1 prime is equal to, well, y1 prime is y prime, but it's also y2. So 0 y1 plus 1 y2. Now that's actually written in reverse of the standard order. I've got the larger subscript on the top. So I'll flip those around to make a nice, neat system here. y1 prime equals 0 y1 plus 1 y2, and y2 prime equals minus b y1 minus a y2. And you could write this in vector form, vector and matrix form in this way. y1 and y2 make up my y vector. I'm taking its derivative here and setting that equal to the coefficient matrix 0, 1, minus b minus a. Times y1, y2. So if you call this this vector here just y with a bar over it or something, we've got y bar prime equals a y, and that looks a lot like the linear equations we did when we were working on just a single equation at a time, like this here. This one is homogeneous because if you put this term on the other side, you'd have y, the vector y prime equals a constant, in this case, a constant matrix, y is equal to a 0 right-hand side. So it's considered homogeneous. And of course, just like we did with single equations, we'll look at how to solve non-homogeneous equations after we've worked with homogeneous equations for a while. So anyway, this is the translation, and the essence of it is just sitting right here. That's it. I think, I don't know that I would memorize that. You know, for me, personally, it's just easier to go through the derivation than to carry around yet another couple of formulas in my head. So I usually just do this when I need to make the translation. So what I'm going to do next is go through a series of examples of these. And you know there's three cases, right? You could have two distinct real roots. You could have a repeated real root. You could have a complex conjugate pair. So there's various things that could happen here. But then there's more than that that could happen, and probably not too surprising because we have now vectors here. So I'm going to show you examples of solutions of these, and then talk about what we can see by looking at the phase plane and the points of equilibrium. Now, let me just mention what the point of equilibrium is for such a system. By equilibrium, we mean this. Suppose this now is modeling some physical system. If you start the system in a certain state, it simply stays there. And if you nudge it a little bit away from that state, it'll come back. So that's what we mean by being in a stable state, in a stable equilibrium. Now, a good example of that would be, I don't know, if you have you can sort of think of like a pencil here. If I hold this up by the end, if I put a pivot point here and just let it dangle down, then I'll show the side view. So assume this is up and down now, indicating up and down. If you nudge that away from straight down, the thing will fall back, right? So that's a stable equilibrium. Now, that would also work with a string. What won't work with a string is, instead of being in this position, you could tip it up here and, you know, balance it. If we're iso-talented and we're dealing with a rod here that's a little bit easier to manipulate than a pen, which has wiggly parts and such, then presumably it's possible to balance such a thing in a vertical position. But that's unstable, because if you bump it just a little bit, it falls over, right? Think of a domino. So it has a couple of different equilibrium positions. When you stand it up on its end, it's in essentially an unstable equilibrium. If you move it away, it falls. But were it hanging down, that's a stable equilibrium. Now, there are other kinds of stability too, and that is what's known as asymptotically stable. So in other words, you start out in a state that's not stable, but really no matter, you could be a very long way from that and still get drawn into the stable state. So that's another situation, but we're going to see all that when we start looking at the phase plane. So let's solve some equations, and that will allow us to look at all that without being unduly abstract. We'll be able to just talk about the details of particular systems. Okay, so examples are next, and this is example 1. Now this one is stated this way. It's just purely review. Second order linear ordinary differential equation with constant coefficients, and it's homogeneous. We know how to solve such things. You write down the characteristic equation, set it equal to 0, and it looks like this one factors lambda plus 4, lambda plus 2, and our eigenvalues are -4 and -2, meaning that our general solution to this homogeneous equation is C1e to the -4t plus C2e to the -2t. Now, in a certain way, you could think of this as being stable if we were to sketch these solutions. Well, it all depends, of course, on the values of C1 and C2, right? But both of these functions decay exponentially towards y equals 0. So if you if you pick a starting point up here, which you could certainly do. I mean, let's say even these were units here. I'm like 1.6 or 7 there. If I set C2 to 0 and I set this one to 1.7, and then when T is 0, I get a 1 here and I'm at 1.7, right? So what's going to happen is this is just going to decay down like that. And the same thing is going to happen if you take negative values of C. Of course, there's subtle differences in the shape that come from taking non-zero values for both C1 and C2. But basically, you have a family of curves that does something like this. Now, this appears stable in the sense that it really doesn't matter how you set the starting conditions. This is all going to be drawn down to basically following the horizontal axis, the t-axis in this case, and it'll do that no matter what. So this looks like stability of some sort. All right, now let's go ahead and translate this thing to a system of linear equations, and we'll solve it according to the methods that we introduced last time. Okay, well, we are going to say that y1 equals just plain old y. Y2 equals y1 prime, and y2 prime equals, well, it's y1 double prime. So our equation becomes y2 prime, I'm looking way back here, y2 prime plus 6y2 plus 8y equals 0. And this allows me to solve for the y2 prime line in my vector equation. So y2 prime equals, oh, and I wanted this to say y1 here. So that's minus 8 y1 plus 6 y2. And then I have my other equation, y1 prime, right here, y1 prime equals y2. So y1, y2 as a vector, take the derivative is equal to, all right, for y2 prime, I have minus 8y1 plus 6y2. And for the top equation, I have y1 prime equals y2. So if we write it with matrix multiplication, as we will want to, it's 0, 1, minus 8, should be a minus 6. y1, y2. So there's our first order system of equations. Okay, now the way we solved this last time was that we compute the determinant of a minus lambda I, which means, roughly speaking, that you look at this matrix here, you subtract lambda down the main diagonal. So 0 minus lambda is here, minus 6 minus lambda is here. You have a 1 and a minus 8, and we're computing the determinant of that. Or you could write det with square brackets, whatever you like. Whatever you like, that's correct. Then when I take this product, I get lambda squared plus 6 lambda. And I need to subtract this product, which is plus 8. And behold, this should look familiar. Lambda squared plus 6 lambda plus 8, I set that equal to 0. And that is the same characteristic equation that I got from this second order single equation. So second order single equation or first order two equations, they are apparently identical. Now, if we're going to write this solution as a system though, our recipe says this: the y vector is going to be any constant times e to the lambda 1 t times the corresponding eigenvector plus C2. Now this could be the same value here, but I can write notation that's technically correct, but you'll find it horrendously confusing. So let's just kind of cheat and make all these subscripts match and say this lambda and this lambda perhaps could be the same. You might have a single eigenvalue with more than one eigenvector. That can happen. Okay, well, that means we need the eigenvalues and eigenvectors. Well, we know the eigenvalues because this equation right here is the same as this equation right here. So we already know lambda is -4 and -2. So you try subtracting those things down the main diagonal and finding the bases of the null space of the corresponding matrix. So we're starting, here's our matrix right here, 0, 1, -8, -6. When I subtract 4, I get, when I subtract -4, I'm adding 4. So I'll have 4 and -2 down the main diagonal, and on the other entries are unchanged. And I'm just trying to figure out, can I find a vector in the null space? Well, by the way, with 2x2 systems, this always happens. Once you've subtracted a eigenvalue, it always turns out that one row is a multiple of the other. So in this case, if you took -2 times the first row, you get the second. So you can figure out your eigenvectors by looking at the first row. Well, for instance, 1 and -4 would do, right? If I took 1 times 4 and then I added -4, I would get 0. And likewise, down here, it's going to work because this is just a scalar multiple of that. So -8 plus 8 is 0. So sure enough, that gives me the 0 vector. So I know that 1 minus 4 corresponds to lambda equals, what was I taking? -4 right there. So when lambda is -4, I get this eigenvector will do. By the way, any scalar multiple of this would also do. Almost any scalar multiple of this. Not if you multiply it by 0, you lose all the information, but otherwise it's fine. Lambda equals -2. Well, in that case, I would be starting with this matrix and adding 2 down the main diagonal. So I get 2, 1, -8, -6 plus 2 is -4. And sure enough, if you multiply this row by -4, you get that row. So if I can find a vector that will give me 0 on the first row, it'll also work for the second. And let's see, looks to me like 1 and -2 would do. So when lambda is -2, there's an eigenvector that works for that. And I'm pausing for just a second because I have to turn the page. Okay, now my recipe for solutions is this: a constant times e to the lambda 1t, that's -4, times its corresponding eigenvector, that'll be 1 minus 4, and then c2 e to the lambda minus t, that's e to the lambda t, which is minus 2t in this case, times that eigenvector. And I need to turn the page here. So y is equal to c1 e to the lambda 1, that's minus 4t, times the first eigenvector, 1 minus 4, or any multiple, and you can see it could be any multiple because we have a c out here, right? Plus c2 e to the minus 2t, that's my second eigenvalue, times my second eigenvector, 1 minus 2. So there's the general solution to the system of equations. Now, especially when you're just getting started, I think it is not a bad idea at all to take this extra step and just write out what this means sort of line by line. Well, it means y1 and y2 are these. y1 is c1 e to the minus 4t times 1. And this one's also going to be a 1. So 1 times c2 e to the minus 2t. And then on the bottom line, I pick up a minus 4, so minus 4c1 e to the minus 4t plus, well, maybe I should have said a minus 2 c2 e to the minus 2t. And just to clarify here, you know, why do you care about the minus 4 and the minus 2 if you just have arbitrary constants in here? And the answer is that these two rows are related to each other. It's true that C1 and C2 are absolutely a free choice on the first row. But once you've made that choice, then you must take a constant that's minus 4 times this one in the second row and minus 2 times the top one in the for the second term. So here's y1 and here's y2. Those are the solutions to the to y prime equals a, whatever we have for a. I need to look it up. 0, 1 minus 8 minus 6 y. And you'll notice that just sitting here, we have c1 e to the minus 4t and c2 e to the minus 2t, and you could pick those off from either row. Those are the solutions that we got by solving the second order ODE in the old way, eta prime. Okay, so that's the first one. Now, I want to talk a little more about representing these solutions. And that is representing them in what's known as the phase plane. Now, the phase plane, people use this in two different ways. Sometimes they mean you have position along the horizontal axis and velocity along the vertical. Or you've got one function here and its derivative graphed along here. But it's also true that, see, if I just look at this form of the equation, I don't have to make the connection that this bottom function y2 is the derivative of the top one. This makes perfectly good sense without that assumption. So it can just mean y2 and y1. And that's how we'll graph it. It doesn't matter what the interpretation is right now. We just want to get a general picture of this thing. Now, if you look at this form of the equation here up at the top, You could just ask yourself a question like this. What would happen if C2 were 0? So I get to just focus in on this one. Well, it's clear that as t tends to infinity, this is going to crush whatever else is in here, right? This thing goes to 0. So we're just going to get multiples of this vector. Well, this vector says that x, along the x-axis, we have proportionally 1, and along the y-axis, we have proportionally -4. If you'd like to make it look a little bit more mathematical, you could say this: x equals s, and y equals -4s. It's just taking s times this vector here. And if you did it that way, that would lead you to the conclusion that y is equal to -4x. Y equals -4x. Well, that's something pretty familiar. We can graph that. So let's see. If you go over 1 unit, starting from the origin, if you go over 1 unit on the x direction, you'd go down 4 units. It's pretty steep in the y, and I get this vector right here. So the original vector is just like this. And you know, if we were drawing vectors as usual, put an arrow there. Don't do that. We're going to use arrows to mean something else in just a minute. Okay, but then I can take any scalar multiple of this, which means I can extend this as far as I want down here, or I could flip it around and extend it. So it's this whole line. Oops, and I did what I told you not to do. I put an arrowhead on there. Pretend that isn't there. Okay, so I got a line here. And what that means is if I set, geometrically, if I set C2 equal to 0, and I chose any old C1 I wanted, I'd land somewhere on this line. And then as t goes on, this thing would go towards 0, which means that whether I started on this side or this side of the origin, the trajectory would be in this direction, towards the origin. Now, what about this vector over here? Well, that's pretty much the same stories, just different numbers. We have x. If I multiplied this by s, that would give me all scalar multiples. X equals s, y equals -2s. So y is equal to -2x. And that is a very similar vector. It just lays down a little bit more. So it looks like that. And once again, if you set C1 equal to 0, C2 to something other than 0, you'd land somewhere on this line, and then as t went to infinity, you get pulled into the origin here. All right, now, if you take linear combinations of these, non-trivial linear combinations, so neither C1 nor C2 is 0, you're going to get a similar kind of effect. It's just that you could start anywhere on the plane. And if you think about it, no matter where you start on the plane, you're going to take a linear combination of these two vectors, and then you're going to crush them both to 0. So it's going to collapse into the origin. And the result is that it's hard to visualize it, but you could approach by any direction, because even though these things are nearly parallel, they are not linearly dependent, so they do form a basis, and that allows you to start at any point and you just crush in towards the origin. This is a point of stability, meaning this: if I start out with this equation right here and I set y equal to 0, 0, then y prime will be 0, 0, and I'll just stay right there, right? The position is 0, the velocity is 0, you're just stuck right at the origin. This kind of a pattern right here is what's known as a node, or sometimes people say a proper node. And this is an example of a stable solution. And by stable, what we mean is no matter where you start, you get drawn into that fixed position. So it's a stable node, and that it concludes this example. All right, next one. Now, after a while, I'm going to do enough of these that the pattern will become clear and you'll be able to anticipate what I'm going to do. Okay, here's another one, y double prime minus 6y prime plus 8y equals 0. Solving in the old way, lambda squared minus 6 lambda plus 8 equals 0. And this factors as well, lambda minus 4, lambda minus 2. Well, this is very similar to the last one. It's just that lambda is equal to either 4 or 2 instead of minus 4 or minus 2. Now, if I were to write down the general solution to this second order linear ordinary homogeneous differential equation with constant coefficients, I would get C1 e to the 4t plus C2 e to the 2t. Now, both of these functions grow without bound, right? So it doesn't make any difference how you choose C1 and C2. Eventually, this solution is going to become unbounded, either in the positive or negative sense. It either shoots off to plus infinity or off to negative infinity. That certainly sounds like an unstable situation. And if this were modeling a physical situation, what we'd be saying is this. Suppose you're trying to set up your system physically so that you're at the same place where C1 and C2 are both 0. But you get it a little tiny bit wrong. So say this one is 0.0000001 instead of being just plain 0, and that one is a hard 0. Well, you're going to have a tiny little coefficient here, but eventually e to the 2t grows big enough to overwhelm this no matter how small that fraction is. So eventually this thing blows up. So it sort of looks like it's going to, in the phase plane, you would expect that it would sort of look like it's going to follow the one of the axes for a while, but then boom, it takes off to infinity. So what happens if we translate this to a system? Well, we want y1 is equal to just plain old y. y2 is equal to y1 prime, then that's one of our equations. We just read it the other way, y1 prime equals y2. And y2 prime is y1 double prime, so it's that first term in the equation, minus 6 y2 plus 8 y1 equals 0. Shoving that to the other side, y2 prime equals minus 8 y1 plus 6 y2. And here's our first equation right here. y2 equals, or rather y1 equals y2. So vector function y is equal to this matrix. Okay, I can get the bottom row easily. It's minus 8 and 6. In the top row, I need to be a little bit careful. This is a coefficient of 1, but it's on y2, not on y1. So I get a 1 here and a 0 here. And once again, I forgot the prime. Really need that. Okay, well, we already know the eigenvalues. And we've done this once before. So I could subtract lambda down the diagonal, take the determinant, set it equal to 0. What would I get? I would get this. And then I would solve it to get that lambda 1 and 2 are 4 and 2. So let's just accept that. We don't need to compute that twice, but we do need to get our eigenvectors. So I'm going to take this matrix, I'm going to compute its determinant after I have subtracted 4 down the main diagonal. So subtracting 4 here, but leaving the other entries unchanged. Why am I saying determinant here? Forget that. I'm looking for eigenvector now. I'm looking for something in the null space. Once again, notice the second row is a scalar multiple of the first. It always is. So once you are clued in, then you realize, it's not so hard to find eigenvectors. 1, 4, for instance, would do. That'd give me a -4 plus 4 equals 0. And that goes with lambda equals 4. The other one, I'm going to take this starting matrix and I'm going to subtract 2 down the main diagonal. -2, 1, -8, 4. I'm looking for something nice in its null space. And let's just double check here. Sure enough, if you multiply the first row by 4, you get the second. So 1 and 2, rather, plus 2 would do. That goes with lambda equals 2. So y equals C1 e to the lambda 1, that's 4t, times its eigenvector, 1, 4, plus C2 e times its eigenvector, 2t, e to its eigenvalue times t, and then the eigenvector, 1, 2. I wrote it correctly, I didn't say it right. And yeah, it looks okay. And that tells me that y1 equals C1 e to the 4t plus C2 e to the 2t. And that should match up here. Looks like it does. And y2 is, you're just going to have scalar multiples there. You pick up a 4 with the e to the 4t and a 2 with the e to the 2t. I should say 4c1 e to the 4t plus 2c2 e to the 2t. And there's our solution without writing vectors. Now, by the way, these two are completely equivalent in a situation like an exam, unless someone asks you to write it in this form. You know, there's nothing wrong with just stopping right there. You got it. It's solved. But I'm writing this so that we are sure to make all the connections. Okay, now we would like to draw draw what I did before in the phase plane. By the way, that has a name, actually a couple of names, but one of the names it goes by is the phase portrait of the solutions. So let's draw that. And let's see, not so much different from before, except we're missing minus signs. In this case, y is equal to 4x, or y is equal to 2x. So y equals 4x, that is like this line, and y equals 2x, not so much different. But they are different. So by taking linear combinations of these, you can span the whole space. So you could start at any old point you wanted. And if you did, you would simply progress along a straight line. Now, into the origin or out? Well, let's think about setting C2 to be 0 and pick a point. You know, how about the point, I think 1, 4 would do just fine, right? So over 1, up 4, maybe that's like here. Whoops, maybe that's like here. But now as t grows, whoops, as t grows, this grows, and so that scalar multiple of the vector gets longer, not shorter. So now you're shooting out of the origin, and whoops, wrong way. Any of these paths are going to do exactly the same thing. Start wherever you will. This system, its solutions are going to blow up. This is also a node. Node means basically that you've got all these points of intersection and you're just coming essentially straight in to the node or straight out from the node, not along some kind of a exponential curve or something. It's a node, but it is unstable. So you'd call this an unstable node. Okay, so unstable node, stable node, we've done both of those. Well, what else can happen? Well, how about this one? Once again, an earlier example warmed over. It's going to change a minus sign pattern. Y double prime minus plus 2y. No, I'm going to change numbers a little bit. Plus 2y minus 8y equals 0, and that needs a prime right there. Okay, in this form, lambda squared plus 2 lambda minus 8 equals 0. Lambda, what, minus 4, plus 4, lambda plus 4, lambda minus 2, factor it. So you've got one negative eigenvalue and one positive eigenvalue. And the general solution is C1 e to the minus 4t plus C2 e to the plus 2t. Now, this one, well, it behaves nicely or it doesn't, kind of depending on the values of C1 and C2, right? If C2 were 0, then this thing is going to eventually come down to the, it's going to come down to the t-axis, or very near to it. On the other hand, if C2 is not 0, and it doesn't matter, positive, negative, and how much, it's going to blow up. Even if this is very, very small, like 10 to the minus 12, eventually e to the 2t will overwhelm it, and this term will become very, very large. So this is not stable in the sense that you could just nudge the system any old way you wanted, and it would, you know, sort of return back to the point of equilibrium. That will not happen. Because if you nudge this away from 0, it blows up. On the other hand, this part of it does. And you do get a little difference in the phase plane portrait. So let's write down our matrix. Let's see. This equation says what? Y2 prime plus 2 y1 minus, rather y2. y2 prime plus 2y2 minus 8y equals 0. So if I push these two terms on, the y2 and the y1 terms on the other side of the equation, I'll get 8 y1 and minus 2 y2, and then on all of these, you always get a 0 and 1 here. So there's our matrix. this says that y1 prime equals y2. So there's our matrix, and we are interested in eigenvectors that come from subtracting, well, either adding 4 down the main diagonal or subtracting 2 down the main diagonal. So if I add 4, I get 4, 1, 8, 2. And it is true that the second row is a multiple of the first. So I'll put a 1 in here and then a -4 in the second. That'll work. That gives us 0. And that goes with lambda equals, what was I doing? I was subtracting a -4. And here, I'll start with my original matrix and looking at my eigenvalues here. I want to subtract 2 down the main diagonal. So, whoops, -2. -2 from this position. And -2, -2, -4 here. And multiplying the first row by -4 produces the second row, so that's good confirmation. I want a nice eigenvector, so that product is 0. Well, how about 1 and 2? And that I did with lambda equals +2. Okay, now let's sketch our phase portrait if we can. This one is the vector 1, -4. So let's see, we have y is equal to -4x. So if you go over 1, you go down 4. Pretty steep. Oops, don't put arrows in there. And the other one is y equals 2x. And that is like this. And now let's take care of the arrows, because that really matters in this case. Okay, for the, oh, I didn't write down the vector solution. Y bar equals, let's see, we've got C1 e to the -4t times V1, which is 1 minus 4, plus C2 e to the 2t times its eigenvector 1, 2. Okay, now, as t grows along the 1, 2 line, no matter where you start, as t gets larger, you're going to expand away from the origin. That gets bigger, not smaller. But along this line, it gets smaller. And now finally we have something to say about this phase portrait that isn't obvious. So if you start at a point like this, so you start pretty close to this vector and further away from that one, the trajectories will come in towards the origin, more or less paralleling this vector. But then after a while, they will turn around and they'll shoot out in the other direction. So these this situation right here is known as a saddle point, which will sound familiar if you've been through Calculus 3 recently. We're shrinking along one axis, growing along another. And you get all these kind of curves in here in a fairly complex way. Now, I could draw these, but what really works better is if I show you how to get them by machine. And fortunately, you can do this from a website. So let's see, I think I have my screen shared. No, I don't. What am I looking at here? Yeah. Okay. All right. Now I hope. Okay. In a strange twist of fate. Whoops. Okay. It's coming back. Don't worry. This takes a minute. In a strange twist of fate, it's working for the people online and not for those in class. Okay, good. All right, I have navigated to the website wolframalpha.com. Wolfram is maker of mathematical software, Mathematica, and I'm going to issue it. And anybody can do this. You just log in here. Of course, you get to look at ads, but I'm issuing the command streamplot. And what I'm going to do is give the 2 rows of my matrix. Now, let me see if I can make this happen here. Probably not. My matrix had rows 4, 1, and oops, the original matrix 0, 1, and 8 minus 2. So what that means is it likes it if you use variables rather than y1 and y2 if you use x and y. So that was 0x1 plus 1y, comma, and then what we're calling y and what in the differential equation we call y2, that is 8y1, which this likes to be called x, minus 2y. And I don't know if it makes it happier. I don't think it matters to the system, but it might be more readable. That came from my matrix equation. Y bar prime equals ax, ay prime, ay. And I just want to graph this along, well, it says minus 4 to 4. So let's see how that does. We can draw it if that scale is not great. Woohoo, there it is. And we do get this kind of behavior that I was describing earlier. So you can see right along here is one of the lines that come from an eigenvector, and right along here is the other. Along this one, the arrows point out, and along this one, the arrows point in. And if you start at any place in the plane, what happens is eventually you end up paralleling this vector that is pointing out. So this is an example, surely, of an unstable solution. So at first, it might look like you're doing okay. You're zooming in towards the origin, but then you turn around and bang, you're out. I don't know, maybe we could. I might get a little bit nicer view of it if I change the scale. Yeah, a little bit. But you can see the behavior. The nice thing about this system is you don't have to think all that hard about which way the arrows point. It'll figure it out for you. So, and for homework, actually, I encourage you to use this. It's readily available to anybody with a web browser. Okay, so that is the that's the analysis of that one. And now that we've seen the picture, we kind of know how to draw these other things in here as well. One here, this one turns around like that. So those are generally how the trajectories work. Saddle point, certainly unstable. Okay, I don't want to run out of time, so I think I'm just going to tell you the results of this one, and we could sketch it even. Now, y double prime plus 16y equals 0. Once you get used to working with differential equations, most of us would pick out pretty quickly that these are sine and cosine solutions. But even if you didn't notice, you know, it's easy to verify. If I take a first derivative on the sine of 4t, I get 4 cosine 4t. And then when I take the second derivative, a negative pops out, and I bump it up to 16 sine of 4t. So it's true. The second derivative of this added to 16 times the original gives 0. Same for the cosine. Now, I did it in class. I carried this all out and eliminated the parameter, got this around to a single equation, and you can show with a little bit of algebra that these solutions are going to be ellipses. I mean, in the phase plane, and you end up with graphs that look sort of like this. And I've forgotten which way they go. If I had my equations in front of me, I could tell. But this is this is an example of what's known as a center. So we've had nodes that are stable, nodes that are unstable, a saddle point, which is always unstable, a center, which of course is always stable. The idea is that once you pick a point on the plane, and let's say it rotates clockwise, then once you pick a point, you stay on that curve. It's fixed. Now, if you nudged it a little bit, what would happen is you just jump to another nearby curve, and you go around parallel forever on that until it gets nudged again. But this is definitely a stable solution, and it's known as a center. And maybe not so surprising. You know, these are periodic solutions. You see the same thing over and over and over again, right? So that makes sense. If you had a truly frictionless environment and you let a pendulum swing back and forth under a beam, it's the kind of behavior you get. It's just back and forth forever and ever. That, it takes a little bit of time to work that one out. If I have time, I'll come back to it, and we can at least do the phase plane using the Wolfram Alpha site. Okay, a couple more that are kind of interesting behavior, and where the website is really quite helpful. is, what am I up to here? Number, example 5, I think. If not, add or subtract 1 and your numbering will be all better. Okay, y double prime plus 4y prime plus 29y. 29 is a prime number, so already looking like trouble, right? Well, let's write out the characteristic equation. And since 29 is prime, there's no way this is going to factor. So we'll have to use the quadratic formula. Negative b plus or minus the square root of b squared, 16 minus 4 times a times c, 29 over 2a. And 4 times 29 is sure more than 16. So 120, let's see, minus 4, 116, subtract 16 is 100. Oh, nice. Minus 4, plus or minus. So I'm getting negative 100 under here. So taking the square root, I get 10i. And then, of course, the whole thing's divided by 2. So I've got minus 2 plus or minus 5i for eigenvalues. Now, we can write down the solution to this second order equation in this way. Y equals, let's see, it's e to the minus 2t when you have a complex conjugate pair. A cosine 5t, maybe I shouldn't say a here, maybe I should say c1, because I don't want that to get confused with a matrix. Yeah, what a mess. Y equals e to the minus 2t times c1 cosine 5t plus c2 sine 5t. Now this part is periodic, so that repeats again and again and again. And this one collapses towards 0. So now it's something sort of kind of like ellipse or circle, but it's getting closer to the origin. So that sounds like a spiral, right? And in fact, that's what you get when you look at these solutions on the phase plane. Let's write down our system of equations. Okay, let's see. We're going to have y2 prime. I'm reading from here. Y2 prime equals minus 29 y1 plus, rather minus 4 y2, and then we get 0, 1 on the first row. Prime y. And we could look at the vectors. I'll grind out one here in just a minute, but then I actually want to switch over to the Wolfram site because it does it so beautifully and so quickly. I know that my general solution is this, C1 e to the lambda 1, which is, well, I can write down a solution, but it's complex value. C1, whatever the corresponding V is, V1 e to the minus 2 plus 5 it plus C2 V2 e to the minus 2 minus 5i. And you could do considerable cleanup on that, but I think what I would rather do right now is take a look at this matrix right here and think about that as the stream plot will want us to say. So 0x plus 1y are just y, and minus 29x minus 4y. And at this point, I'm going to switch over to the website. Okay, so the first row basically doesn't change on these. They're always the same, but this one does. So I've got minus 29 x minus 4y. And let's go back to minus 4 to 4. By the way, if you can't see that on the screen, this is just coded as x equals minus 4 dot dot 4, comma, and then the same for the y. And there we are. It is a spiral, sure enough. It's not so easy to see here. So how about if I expand the along the x-axis? Let's go from minus 1 to 1. So we're distorting this by stretching it along the x-axis. And here you can easily see that it is indeed a spiral, and you can see which way it's spiraling in. So the phase plot, or phase portrait, more or less looks something like this. In this case, it was spiraling in a clockwise direction. This is called, surprisingly enough, a spiral, and this one is stable because it's spiraling in. Now, notice you could actually predict that here. You have minus 2 as the real part of this of eigenvalue. If that had been a plus 2, it would spiral out. So that would be an unstable spiral. And let's see, I think I've hit all the main ones right now. So how about this? I'm gonna do one more example to, I'll do an unstable spiral, but I'll actually fill in all the details and show you how to do this to get real solutions. And it's longish, but it looks a lot like things that you've done before. So what was I on before? Already forgot. Example 5, this must be example 6. Y double prime minus 4y prime plus 29y equals 0. This is just like the last one, except I've switched. Before there was a plus here, and now there's a minus. So lambda squared minus 4 lambda plus 29 equals 0. Lambda equals 4 plus or minus. It turns out to be exactly the same that it did last time. Minus 100 over 2. So I'm not calculating this with blinding speed. I remember, I did it earlier. So it's 2 plus or minus 5i, which is different from last time. Last time we had a minus 2 plus or minus 5i. Okay, so let's write down our matrix A. The bottom row comes from the original ODE. So when you push those things on the other side and reverse their order, you get minus 29 is going to be the coefficient on Y1 over here, and then plus 4 is going to be the coefficient on Y2 over on the other side of the equation. And then, having done this enough times now, we know you always just get 0, 1. And we would like to get eigenvectors. Can I? Boy, those are ugly. Well, you know, I think I won't do this one in detail. Let's go ahead. Let's go back to the website. I mean, we could struggle with it and probably get something that's pretty convincing, but well, there's easier ones to choose. So okay, everything's the same as before except a plus here. And remember, we've got the scales distorted, so it's actually stretched out in the x direction, but that probably will make it easier to see. That one, the old one, is clearly spiraling in. And this one is spiraling out. So in this case, you get an unstable spiral. Okay, I think, oh, I do. In my notes, I have buried some examples that are not too bad. I thought. Oh, look at that. I think this might do. Before I forget it though, I do want to report this. You can make a chart for classifying the equilibrium point, and it just goes by the eigenvalues. Now, this is for a 2x2 system. Equilibrium points are also called fixed points, because once you land on them, you stay there. Okay, if the real part, if you have two real eigenvalues, lambda 1 and lambda 2, by the way, real is actually implied by this. Complex numbers are not simply ordered. Pick two complex numbers, one may or may not be bigger or smaller than the other. So if you have two complex eigenvalues, then your equilibrium point or your fixed point will be an example of an unstable node. If you have two real eigenvectors and they're both negative, then you have a stable node. And maybe I could kind of put a little sketch over here for at least some of these. Unstable node means all these are pointing out. But notice, you can come in, or you can go out at any direction. Stable node, similar, except you're going in. Okay, now they could have opposite signs. So these were two real eigenvalues. So what if you have two real eigenvalues now, but their product is negative? Which is a fancy way of saying one is negative and one is positive. In that case, you are definitely looking at a saddle point. And the phase portraits are generally, you know, sort of kind of like this. Along one axis, the trajectories are coming in. Along another one, the trajectories are going out. And curves, solution curves, tend to look something like this. They come in and then they shoot out. They come in and then they shoot out. And that looks like a sharp corner there. It's always a curve. Now, if they are complex, you always get a complex conjugate pair. Continuing my table here. If the real part is greater than 0, then you have a spiral which is unstable. If the real part is less than 0, then you have a stable spiral. I won't treat you to another of my fabulous figures there, since it's just like that, only it's coming in. Well, maybe I should draw it. It's conceivable somebody might forget. Now, I think this is true, but I didn't look it up, and I didn't try to prove it. If the real part is 0, you'll have a center. So you get an ellipse of some kind for the phase portrait. These things, a stable spiral and an unstable spiral, the stable spiral, some people call this asymptotically stable. And what they mean is, you know, it's not like you're on a fixed track and you're just always going on in the same groove, but rather you're converging to a particular place in the phase plane, and you're approaching it in the limit. So those are the major classifications and how you can tell. As I was doing these examples, once I had the eigenvalues, I knew whether it was going to be stable or not, and whether it's going to be a node, saddle point, or a spiral.
Do you tend to describe these cases of the spirals? Are they describing something like simple harmonic motion?
Yeah, the question is, do these spirals describe something like simple harmonic motion? The answer is they are describing, if it were a physical system, we're talking about motion now, as opposed to, say, electrical circuit, then you have motion that has some aspect of periodicity to it, keep going around, but you also have an aspect of decay. So it's not quite simple harmonic motion, but it is like it. You know, if you take simple harmonic motion and then you crush it inside of a exponentially decaying envelope.
So like a real pendulum.
Yeah, yeah. Mm-hmm. Now, if you do a phase portrait for a real pendulum that has, well, a real pendulum, what you'll find is you'll have some solutions far from some central envelope that sort of look like this. And then you have other solutions that spiral in. And these guys, if they get too close, they get sucked in. Now, physically, where that's going is fairly easy to figure out. If you take a pendulum, a real pendulum, and you have nice clear space all the way around the beam, really good bearings, and you just give it a tremendous push, what happens is the pendulum will just zing around. You know, it doesn't go back and forth along the bottom. It goes around and around for a while. That's this. And then finally, when the amplitude decays enough, it starts going like this and decays down to zero. So these kind of figures are easy to type into Google. Phase plane pendulum. You'll see the pictures. And if you have a driving force, you get something like this too, but it tends to kind of tilt it to the side. But it's still, as long as the driving force is not too great, you do get this kind of behavior. You know, any excessive velocity at the beginning attenuates, and then you're back down to a pendulum that's just swinging back and forth. Okay, I think I said I had, yeah, I do. This one I think will work out in a reasonable amount of time. Now I should maybe make just a general comment on this. On finding eigenvectors, this might actually be more important than what I had in mind. So I think I'll spend a little time on this, and that probably will just exhaust our time in class. Finding eigenvectors. I'm not saying eigenvalues, so I'm assuming that you have the eigenvalue already. Now, if you have even like a 3x3 matrix, so you know I'm not committing myself on what the numbers are in here, but you've got a 3x3 matrix, and you have subtracted some lambda down the main diagonal, and now you want to find the eigenvector that goes with it. What you are probably not going to do is what I was doing before. I stare at it for a while and, oh, I see the answer, so I write it down. Well, if you have a 3 by 3, but surely like a 5 by 5, it's just too darn hard, right? So how do you figure out what the eigenvectors are? Well, this is actually a problem that you already know how to solve. You are trying to solve a homogeneous system of linear equations. So how do you do this? Once you've got a definite matrix here, now I don't mean with lambda as a variable, but once you've got fixed numbers in here, then you simply write down your matrix and you row reduce it and you write down the systems just as we did before. Remember, I used to say in instructions something like, find the solution in parametric and vector form. That vector form, those vectors are your eigenvectors. So that's how you do it. So let me just make up the next to the last step here. Suppose on this one, I come up with something like this. X1 equals, well, what do these things look like? Now it would have to be a zero, a leading zero here. I'm not going to have just a constant because this is a homogeneous system. So maybe I've got something like this. 2s minus 3t, x2 turns out to be s, and x3 turns out to be t. Well, in vector form, my vector x equals s times 2, 1, 0. Plus t times minus 3, 0, 1. Those guys right there are eigenvectors. So you can do those by hand. You can also check them with MATLAB. So I'm going to go back to screen share here. And let's see, I also have this website up. It's called octave-online.net. You can, it timed me out, but I can start again. I can write Octave or MATLAB commands right here. So for instance, suppose I'm just going to make up a matrix and it's not going to have nice eigenvalues probably. Actually, what I'm going to do is I'm going to make one that will not be too awful. And I'd tell you my trick, but I don't really have time. Okay, so I got a temporary matrix there, and I'm going to set A equal to temp. Now, this part of the trick is easy to understand. Plus, this doesn't mean derivative. It means it's transpose. So I've got a nice symmetric matrix here. Symmetric matrices always have real eigenvalues. So there is a very nice command available in the system, and it will give you a matrix of eigenvectors, and it will give you the diagonalized matrix with the single command EIG, EIG. So do the eigenvalue analysis for matrix A is what that means. And you can see along here, I have columns. Those are eigenvectors, and they correspond to these eigenvalues. Now, sometimes those eigenvalues will be something that's pretty recognizable, and sometimes they won't. You just, you know, you have no idea what the darn things are. So if it falls into the latter category, well, there's nothing you can do but just report the numerical expressions. But sometimes they're quite nice, and you can figure them out without too much difficulty. So let me modify my A. What did I have here? Let's do this. A, first row, all columns. I'm gonna change the first row is what I'm doing. Make this 2, 0, 0, just like something in the homework. And then I'm gonna make a first column, all rows, equal to, well, it's just the transpose of the first row. Okay, so I've got, this is a block diagonal matrix, but one of these blocks just has one item in it. So this will have a nice set of, well, maybe I can't. Oh yeah, I can. This will have a nice set of eigenvectors, I think, at least nicer. So you can see these values here. One of them is clearly 1, 0, 0, right? And the corresponding eigenvalue is 2. So this first column is an eigenvector that corresponds to the eigenvalue 1.5279. Second column, eigenvector corresponding to eigenvalue 2, and similarly for the third. Be aware of the fact that sometimes you will get a result that will say something like, well, how about 3 point, a string of zeros and a 6, plus, I don't know, 2.4 times e to the minus 12i. That is probably not a complex number. You've got a tiny little bit of round off error there, and it's probably just the number 3. So just be aware that some of these, especially as the size of the matrix gets big, there's quite a bit of computation involved, and you can get round off error. And if you get a result that looks like a number with a real number reasonably sized with an eensy-weensy tiny little imaginary part added on, that imaginary part is probably really zero. So now, you know, you're guessing, but it happens all the time, so you should be aware of it. Okay, well, that is, where did my video go? Okay, that's the end of the lecture. I could show you more, but honestly, you could have a whole course on this. So it's got to stop sometime. And I have shown you as much as you'll typically find in books designed for engineers and scientists. So it's a start, and you know, you can devote your life to this. If you do, it's a worthy pursuit. All right, I'll see you on Thursday. I have posted the next homework assignment, but I got off my schedule somehow and forgot to put it up until today. So it's not actually due until next week on Tuesday. We do have people that work full time, and they need to have a few days. Don't forget, the second exam is next week on Thursday. So getting caught up on homework is a great idea, and I will try to do the same. All right, see you next time.
I forgot to pick that up last week.
Oh, shoot. I didn't bring papers with me. Would you mind sending me an email?
Yeah.
And just telling me that you didn't get your paper back, would I please look for it? And if I have enough time, if I find it, I'll scan it right away.
Oh,
and email
okay.
it to
Yeah,
you
that'd
so
be
you can
great.
see it.
Yeah.
But I'll also try to get the original back into your.
Okay, perfect. All right, I'll do that. Thank you.